want to thank the organizers for this wonderful workshop. It's been great already. So let me just start. So my topic is non-Gaussian tails and primordial black holes. And this is work that will hopefully appear before we get into those infrared divergences that Cliff talked about. We'll see with Mirbabai, Panagopoulos, Leonardo, Senatore, and Zaldaryaga. Okay, so the plan of the talk is to introduce and motivate the subject, to give our basic model of this effect, and then, time permitting, to explain some interesting formal analytic results in quantum field theory that we derived along the way toward this result. Okay, so non-Gaussianity has been studied quite a bit in our field. So if we imagine that we have the scalar perturbation zeta, which is related to an inflaton fluctuation in the usual way, but also some transverse sector of fields that I'll label chi, then we're interested in understanding in field theory and measuring as much of as we can the probability distribution for zeta, which in general would be given by this very general expression tracing out the extra scalar field degrees of freedom that we don't observe to obtain the density matrix for zeta, which we do observe. And this is an enormous functional of a field, which is a very broad starting point, and one would like to understand how to make the most of it. Now, of course, if we take the couplings to 0, and we also work in the ground state, so the Bunch-Davies state, then this whole thing collapses to a Gaussian. But in general, it's not. And the question is, so if we're close enough to that, and part of the question is how close do you need to be, then it leads to observables that are these low point correlation functions that have been studied quite a bit and constrained. And already at this level, of course, there's interesting shape dependence, even for the power spectrum and also, of course, for every low point correlation function. Okay, now let's think for a moment about the opposite extreme, which is instead of low point correlation functions, let's consider large endpoint functions, so zeta 1 to zeta n, and related to that, the tails of this huge distribution. So in various pre-existing works, these higher point functions have been seen to play a role. So one example was just alluded to by Daniel, which is that if you have particle production in the context of systems with a shift symmetry, a discrete shift symmetry, one finds basically that this object scales like some underlying coupling, which could be weak, times the frequency of the discrete shift symmetry breaking to the nth power, and that, when you then do some combinatorics, gives you a kind of best n, which is not necessarily the low point correlation functions that we've focused on in the field in the past. So that's one place where this has a meaningful answer. And more generally, let me just write it over here. If you look at just quantum field theory abstractly, we know that endpoint functions of fields, let me just write it as some field phi, that at least at the classical level, these things grow like some coupling to the nth power, but with an n factorial enhancement. And what I mean here is the connected diagram. And quantum mechanically, it gets very difficult to understand how far this behavior persists. But one of the lessons of our investigation is that in the context of multi-field inflation, this is quite calculable. And indeed, this does persist. So the question is, how far does that go toward observables, which is a very large question. But for now, let me, with this very general motivation, move to, sorry. Okay, there we go. Sorry. Okay, so let me go to the main idea of this talk, which is that non-Gaussian tails, when they do exist, and we'll see that in multiple field inflation, they are rather common. This would suggest that at least a very good observable to study regarding these would be rare events that are sensitive to the tail. In particular, let's focus on primordial black holes. Okay, so very quickly, for a black hole, you need the density to be bigger than some critical density. It is sufficient to think about this in terms of a perturbation of zeta, which is bigger than something like 0.1, as was determined, in explicit calculations of black hole formation by, goes back to work of Bernard Carr, but recent investigations like Harada, Yu, and Corey in 2013 have really nailed down what is required. And basically, some perturbation that is, let me say it like this, large enough in the scalar perturbation zeta will lead, when this crosses the horizon, to a black hole. Now, let's get some very basic relations straight before going to the model, which is part of the point of this talk will be that the scenario we have in mind gives a seemingly very natural and simple mechanism for this. Whereas in the past, it seems that a lot of the model building has involved introducing a spike in zeta to go from the 10 to the minus 5 to 1 or 0.1 by kind of modeling in a huge spike in the perturbations at some point, at some scale. Whereas we're finding that's not really necessary. And I'll show you where this comes from soon. Okay, so basic equations for the resulting black holes are as follows. So we want to know the probability of such an excursion with, let's say, some size r star, some proper size r star. So then the Schwarzschild radius of the resulting black hole will be basically the Hubble size at the time of horizon reentry, TH, which is evolved, of course, from our star by the expansion of the universe. So in our context, what I will get to is a mixing between the chi sector and zeta, which will happen at a certain time, basically at the end of inflation. And we need to evolve the probability distribution that we start with at that point to the time of horizon reentry. And if you do that and assume radiation domination, with just a couple of steps of algebra that are probably familiar to many of you, to give you this general expression for the resulting black hole. That's to say, if you have an excursion of this form, then you get a black hole of that mass. And an abundance, which is commonly denoted beta, which is an integral from this critical value to infinity of the value of the field smoothed on this scale r star to not pick up any spurious contributions times whatever the right probability distribution theoretically is for that variable. So, so this is the mass, this is the abundance, and this is basically constrained, you know, observationally by certainly not over, it can't exceed the dark matter abundance. So let me write this as 10 to the minus 20 times the square root of the ratio of the mass to the mass of, you know, 10 to the 15 grams, at which the thing would have evaporated. So this is the kind of constraint to have in mind. It's a small number, but not an arbitrarily small number. And so the question is, from that enormous functional, what is the rate of this kind of event? So now let me consider, as I already said, a situation with two sectors of fields. This field, sector chi, which will include, you know, some number nf of them, which, let's say, evolves separately, evolves independently, and as a probe on the underlying inflation until it mixes with the scalar field which is related in the usual way to zeta. So delta C critical in the sense of the discussion over there is basically 10 to the fourth. And let's consider a scenario of this kind. Now, non-Gaussianity could be introduced in either or both of the evolution of the field chi itself, or the mixing with the other sector, with the inflaton sector. Now, let me actually start with the mixing and write down an operator in the interaction Hamiltonian that is a very basic higher dimension operator that respects, for example, a ONF symmetry that connects to the inflaton in this manner. So perfectly natural mixing is the first thing you would probably write down. And this thing occurs, let's say, over some time scale delta t, which is going on at the exit from inflation. So let's see if I can do this. Perfect. Oh, there are three, but okay. So what are we doing? Okay, so we have this statement, which is quite general, and I want to apply that to this scenario that I discussed up there, where we have this independent evolution and then we mix. So let's look at the time evolution during the mixing. So we have this mixing interaction that I wrote up there. And of course, we take the phi squared, and we can expand it to the background phi plus delta phi. Something like this. In other words, the first thing that we encounter is the coupling between the perturbation delta phi dot and chi squared. Now this is proportional to the field momentum. And so the evolution operator over this time step delta t is very simple. It's e to the minus I delta t times the Hamiltonian, which can be written in terms of the field momentum in this manner. And what this is, it's a translation in field space. So we can immediately obtain a relatively simple form for this rho of zeta, or equivalently rho of delta phi, where we recognize that this, first of all, factorized into some transverse evolution of chi, which we have not yet characterized, times the Gaussian evolution for delta phi, the usual Gaussian for the inflaton field. So we have this time evolution step in which we shift in phi field space. So that we can immediately see gives us this convolution of a Gaussian shifted in field space where kappa I've defined as this coefficient that we read off from the mixing interaction that I just wrote down. Okay, so this is the form of the probability distribution for the scalar. It is a convolution so far, but what we see here is two things. First of all, this mixing interaction kappa comes with a boost by, if we put everything in terms of in dimensionless units, it comes with a boost by the 10 to the 5th of the familiar scalar perturbation. So this kappa can actually be naturally quite large, up to the point where we might lose control over these higher dimension operators. And that's a bit of a detailed question. Second thing to note is that if we ask the question about the tails of the distribution before we mixed with this extra field sector chi, then we would have this rho. So this by itself, so let me compare to the Gaussian, which roughly speaking by itself is just going to do this without any mixing with chi. And in that case, if we took our diagnostic for black hole formation and applied it to the Gaussian of phi by itself without any extra contributions, then of course this would go like e to the minus 10 to the 8th. So it's just ridiculously small and nowhere near large enough to produce a black hole. So this thing by itself, without the chi, would be absurdly small and not have a tail of interest. But what can happen inside this path integral for a wide variety of things here is that this piece can cancel that without loss of generality. Easier to think about perhaps this sign of this. So this piece with this boosted kappa mixing coupling can cancel this, and then we're left with whatever suppression we have over here. So that's more or less the general picture. And which one are we on? Okay, so we can use all three, right? Okay, so now let's talk about this chi sector by itself. So that's this other factor in the path integrand that we have. And the first case to consider is to take this thing to be simply a Gaussian. For example, it could be a massive field. So it could be a system with a simply with a massive field with a mass of order 3/2 Hubble, this kind of system that Dan was talking about earlier. And even there, with this mixing, you can see that there's a non-Gaussian tail. So let's draw this picture, which was the worst drawn parabola ever. Okay, so we can think about the chi sector very intuitively before bringing in the more sophisticated methods, the kind of thing that Cliff was talking about earlier. So at this level, what we're interested in is rare excursions to large values of this chi, large enough that, again, kappa times the chi of the tail should be this critical value of the scalar excursion needed to form a black hole. And if we think about this Gaussian model, well, the probability for such an excursion in chi is some Gaussian thing of order 1. And then these excursions, depending on how large they are, depending on how large the R star is, will either have time to evolve inward by a lot or not. And in fact, from this picture, it seems clear, although it took some of us a while to understand this, is that therefore you really, for this kind of inward drifting potential V of chi, the best you can do in terms of getting out to the tail is consider the short modes that come out the latest, and which therefore don't have much time to drift back in. Okay, so that's a kind of heuristic argument for something that seems to be correct from the more sophisticated treatment of stochastic inflation in this sector and so on. In fact, at least if you consider anything, as we often do in more high energy physics, things that are flattened relative to this. In fact, if we consider models of the form chi to the p, we can go down in p, as typically happens by energetic adjustments, and continue to have this behavior. There is one condition that's important for this business of PBH. So to have a large mixing between the two sectors, but not to screw up what we know in the CMB, we need the 2-point function at CMB scales to be sufficiently small. So let's write that as in kind of suggestive notation. It's some power law one finds in the kind of treatment of the scalar fields that Starobinski introduced that we'll hopefully be able to discuss later. And this lambda is a parameter there that has to do with the gap in a certain equation for the field, which for the massive field is basically m squared. And we need this to be 10 to the minus 3 times the usual one to not infect it with any extraneous contributions. So that puts some condition on this scenario, but it's a pretty weak condition. So let me whoops. Yeah. Sorry. Sorry. I'm not sure what I did to the screen, but anyway. All right, so let me put this together and explain the black hole abundance in this context. Okay, so we have this probability distribution for the scalar field. We can view it as a distribution at this R star of order Hubble. And so basically we have something like this. And let's see, yeah. So we need to impose that this be sufficiently small on the tail to have a viable abundance. And once again, the idea is simply that chi within this integral can cancel the otherwise enormous suppression here and leave us with a weaker suppression from here. Okay, so let's just see how that works. First, just making a simple estimate for that. So here's the configuration of chi at this scale R star of order Hubble that will kill the enormous tail excursion in the scalar field related to zeta. And so plugging that back in, we can see that we're going to have a estimate for the density here, or for the probability on the tail, which will go like delta phi c over kappa, basically to the nf over 2 times something which is linear in delta c. So just as a picture, there would have been the Gaussian. Now at some point there's this linear tail that pokes up above the Gaussian. And furthermore, there's some measure factor here that is enhanced if we have multiple fields. Okay, so that's basically the answer, but let me write down an analytic expression for the abundance in this model. Where, as we said at the beginning, we integrate from the tail on out. Here y is a variable, it's basically chi squared. Gamma here is a fudge factor that dictates exactly what that mass was in the massive case, and so on. So this is, of course, a simple known function. Okay, so let's take a look at this integral. If we had the lower limit going to 0, we would get the entire probability of 1. So notice that beta would go to 1 as this lower limit went to 0. Now, we can combine that observation with the fact that there's a nice saddle point estimate of this integral. Just do it here, and you see, of course, that the y value that would be a saddle of this integral is of order nf. And that's okay if that saddle in this y integral is on the contour. So in that context, for enough flavors, you can see that there will be an abundance that's not only detectable, but it's immediately excluded. So that shows that for such cases, which in particular means this, this would produce PBHs, and not only would it produce them, it would, again, immediately exclude that region of parameter space in terms of the number of fields in the problem. So how many fields should we expect? Well, of course, we don't know. So, in the standard model, there's 4 or 10 independent fields. In the string landscape, formally, there's an infinite number. They're not all light, but so it's hard. For me, it's hard to tell where to put the sort of theoretical expectation on that. But in terms of the calculations, basically what happens is that even if we impose the most strict theoretical bounds on our kappa, so remember we had this kappa that had some prefactors times something that's large. So, but if we insist that the classical corrections to the mixing interaction I wrote down can be immediately excluded, even then we get PBH production for NF a bit lower than order 100. And if you reduce kappa or kappa times this gamma fudge factor, if you increase kappa, the number of flavors for which you have sensitivity goes down correspondingly. Okay, so that is kind of the simple PBH production mechanism that I wanted to explain. There are some formal lessons that we learned in this investigation as well, which I could come back to, at least to list them for you. Although it doesn't look like there's time to really explain either one of them. So let me at least mention them though. So formal developments. So one of them is that in this context of multi-field inflation that is mixed, let me see if I can say this quickly. The n factorial enhancement is ubiquitous. So of these correlation functions, it's very generic for them to have a factorial enhancement and hence a tail that pokes above the Gaussian somewhere. And of course, the question is, how big is it when it does exceed the Gaussian? So you can get at this by calculating the generator W of J of these connected correlation functions. In this context, that is a very simple exercise. Which and as you can see from this expression, this part of the problem here is a Gaussian integral. It's doable. You can do that integral, make a saddle point approximation for the chi integral, and very quickly see that in order for to avoid this conclusion of the n factorial, so you analytically can do this delta phi integral, and then you have this chi integral, and there's a saddle for this integral, which is a function of J. And if we write this rho chi as e to the minus s of chi, just without prejudice for what it is, you find that plugging this saddle into there, in order to avoid the factorial enhancement, this s of chi saddle would have to be an entire function of j in the complex plane. And that's very constraining, and it's not true of kind of garden variety potentials that you would tend to write down. So that was one lesson. Another one has to do with the nonlinearities in the chi sector itself. So happily, Cliff reviewed quickly the Starbinsky approach to that problem, where there's a very nonlinear PDF for the long wavelength modes of the problem. And in general, in the Starbinsky work, including the paper he wrote with Yokoyama, you can compute, in principle, you can compute various probability distributions for the field at various points, or rather in various patches. And one fun fact for those who are interested in analytic methods is that if you consider, instead of this quadratic model, if you consider a linear model, and just let it have this cusp at the origin, as I've drawn it, that becomes an analytically tractable case in which to make all these calculations in the stochastic inflation framework. So for example, let me just bring down, I'll just erase this. So for example, when it comes to understanding the way that the system approaches their equilibrium distribution, and related to that, the way that the Green's functions die off with scale, has to do with certain gaps in a Schrodinger problem. So Cliff wrote down the Fokker-Planck equation for, say, rho 1, and if you write that in a nice way, you can derive its component functions from some Schrodinger problem that I think many of you know. With coefficients here that are known. And for this model with a linear potential, this effective potential W of chi is extremely simple. So for this model, W of chi takes this form. There's a delta function at the origin, and then a gap to a continuum of modes. So these guys are plane waves with appropriate boundary conditions at the origin. And not only the one-point PDF, but in principle, the endpoint PDFs and the correlation functions and so on are analytically calculable in this model, which is a fun feature that also helps us understand a bit more about what the field is doing and how, for example, how the probability, how the joint probability to go from the tail down to 0, which is the kind of thing we need for black holes, under what circumstances that factorizes on what size of patch, and under what circumstances it doesn't, and so on. So all of that is analytically tractable in this example of Starbinsky. But basically, we think that this black hole mechanism occurs pretty generically with the features that I described, at least for the potentials like what I've drawn, where the drift is inward. Let me end with an open question, which should be interesting given this, which is to ask about, and there have been some interesting papers sort of related to this. So let me say it like this. What about outward drifting? Potentials v of chi. So again, just to explain where this is coming from, there's two sources of nonlinearity a priori. There's the chi evolution by itself, and then there's the mixing. The mixing was sufficient to give these black holes. And for inward drifting examples, our understanding is that you just fluctuate out as you would for short modes. It's governed by the Gaussian, and you drift in the least in this kind of potential if you indeed consider the short modes. So that led to a black hole phenomenology whose mass scale is basically determined by the Hubble scale of inflation, which is the scale at which we mix. But that argument is a bit too quick if you consider outward drifting examples, so examples where, like some of these oscillatory things are just symmetry breaking, where your fluctuation out to a large value of chi could land you in a regime where you then drift outward. And in that case, there's more of a preference for longer modes. So that's an open, but presumably quite tractable thing. In fact, it could be studied using this simple analytic model. OK, so let me stop there.